So, what is multiple linear regression? Multiple linear regression is used when we want to make predictions about a continuous dependent variable, also called an outcome variable, based on more than one independent variable, which is also called a predictor variable. Welcome to regression. We use different words, even though you're probably used to DV and IV. This is a parametric test, which means we assume normality of the residuals. So we're going to build our model first and then check the residuals of the model for normality. So we have to meet this standard bell-shaped curve, and this is checked on the residuals. If you were looking for additional help running multiple linear regression, we have some details for this in the University of Guelph SPSS LibGuide. There's also the Laird Statistics Guide, which is quite good, and the SPSS documentation. What are the assumptions of multiple linear regression? We have 8, so we're going to check these today. The first is that your outcome or dependent variable must be continuous. The second is that your predictor or independent variables should be continuous, approximately continuous, which is some ordinal data if you're taking Likert questions and doing like an average, or the data must be dummy coded if you're using a categorical predictor independent variable. Our third is that you must have independence of observations. Our fourth is that there needs to be a linear relationship between each of your predictor variables and the outcome variable, as well as there needs to be a linear relationship between your predictor variables, all of them together, and the outcome variable. So we'll check that one. 5, 6, 7, and 8 all have a star next to them. This indicates that we build our model first, we build our regression model, and then check these assumptions. So 1 to 4 we check in advance, 5 to 8 we check after we build the model. So for 5 we have homoscedasticity, for 6 we have no multicollinearity, for 7, we have normality of the residuals. And for 8, we have no significant outliers. Some of these might be new, even if you've come to the workshop series. So let's cover these in the next few slides. All right, assumption number 1, your outcome variable, also known as your dependent variable, must be continuous. So if we were using, for example, fake data 1 in our fake data set, we can look at this variable and say, we've got a bunch of decimals, we've got a range of values. This passes the assumption. This is a continuous predictor variable. By predictor variable, I've already made a speako. This is a continuous outcome variable. This is our dependent variable. So we've passed this assumption. Our second assumption is that the predictor variable must be continuous, approximately continuous, or dummy coded if it is categorical. So for example, if we were using fake data 2 as one of our predictor or independent variables, we can look at this variable and say, we've got a range of values, we've got decimals, this is a continuous variable. This one passes the assumptions. We could also use, new for this week, a categorical variable. So we could use our gender column, for example. This has male and female participants. They're actually already dummy coded as 0 and 1. So we've got our dummy coded information here. So we match this assumption. The trick for you, if you're watching this after the fact, is if you've got a categorical variable with more than 2 groups, there's some resources you're going to want to read about how to dummy code this appropriately. It's going to be number of groups minus 1. We're not covering that today. It's a little bit too complex. If you have questions about that, feel free to use the information at the end of today's workshop to come and book an appointment with me. So we've passed our assumption here. We've got a continuous predictor variable, and we've got a dummy coded categorical predictor variable. So we're good. Our third assumption is independence. So each observation or each row in our data set should be a unique participant, for example, if we're working with humans. So if I look across row 1, this participant identifies as male. They have information for fake data 1, fake data 2, fake data 3, etc. And they're a unique participant. This is fake data. We know that this matches our assumption of independence because I say so. If this is a real data set, it's a little bit harder to check this at this stage. You would normally make sure you have independence before you actually collect your data through things like making sure only one response per survey, for example. All right, so in our fake data set, we've passed this assumption. It's a little bit hard to check if you've already got a data set and you haven't checked this in advance. Our next assumption and our final assumption that we check before we build the model is our assumption of linearity. So the easiest way to check linearity is actually to make a graph. So we can say graph, chart builder. You'll get a pop-up that essentially asks you to make sure that you've set up all of your measures properly for your variables. So make sure you've got continuous listed as scale. For this, I've given you the fake data set. You're welcome to say, okay, we've passed that. So what we're going to do for linearity is we're going to check each of our predictor variables against our outcome variable to say, does this look like a line? And we're going to do the combination of any predictor variables with the outcome variable. So we're going to have to make 3 different graphs here. So let's go. If you are using the chart builder for the first time, it's a little unintuitive. You have to select which kind of graph you want first in the bottom left. So we're going to click scatter/dot. The next thing you do is, based on the options it gives you, you have to look at them and say, which one does it look most like I'm trying to make? Ours is this first graph here. We click on that and we drag it to the blue text in that big box in the middle of the screen, and it should give you some fake data, and it says it'll look approximately like this. So we've got our scatter plot. The next thing we have to do is say, which variables are we using? So we're going to use fake data 1, and we're going to put that on our y-axis. And we're going to use fake data 2, and we're going to put that on our x-axis. So we're picking right now 1 predictor and 1 outcome variable. When you've got everything set up, you say, okay. And that will give you a graph that looks something like this. Yours is going to have blue points. Mine has red because I made them red for the presentation. So here we're looking for a linear relationship between our 2 variables. We want to see whether the points roughly form a straight line. It might be going up, it might be going down, but we want it to look like a straight line generally. If I squint a little bit at my graph, the left side looks kind of like it's trending downwards, and the right side looks like it's kind of trending upwards. So we actually might have a bit of a U shape going on here. So linear regression might not be appropriate because it doesn't actually look like we've met the assumption of linearity here. Just to demonstrate and to practice today, we're going to proceed with the regression anyway, but this is your warning to always check your assumptions. You don't know if you pass your assumptions unless you actually check them. If you wanted to add a line to this graph to help you visualize what's going on, to be able to ask, is it actually a line? You can double click on the graphs in SPSS and it will open up another dialog box. So this will open up our chart editor. And there's a button that you can click that will help you add a line to help you visualize whether it's a straight line or not. So there's 2 different rows of buttons in this chart editor dialog box. On the second line, kind of near the end, it looks like a scatter plot with a straight line through it. If you click that button, it will pop open a new dialog box for you that by default adds a straight line to your graph. You could use that option. It's the linear option. The other option you could pick right beside that is called LOESS, L-O-E-S-S. A LOESS curve measures this in a slightly different way. And if we click LOESS as our option, what it's going to give us is a graph that looks something like this. So the LOESS curve does things by moving windows. So it'll check, for example, 5 points, draw your line of best fit, move the window by 1, draw the line of best fit, move the window by 1, draw your line of best fit, all the way through your entire data set. So instead of doing your best guess of a straight line through everything, it's doing it in little chunks. And when we look at this, we can say, does this look like a straight line? Well, the second half looks pretty straight. It's going kind of up to the right. Everything looks good. The first half, the stuff on the left, that doesn't really look so much like a straight line. So that might give us an indication that we have not met the assumption of linearity. It doesn't have to be perfect. In a lot of stats, we're just kind of like eyeballing the graph. It doesn't have to be exactly a perfect straight line for you to ever be able to use this test. But if I look at this one, I'd be like, ooh, maybe we haven't passed linearity here. So we've checked one of the 3 graphs we need to make. We can go back to our chart editor. And in our chart builder, same thing, we're going to pick scatter plot. We're going to pick that first graph, drag and drop it. We can grab fake data 1 and put it on our y-axis. We can grab gender and put it on our x-axis. Reminder, this is our categorical or dummy-coded gender variable. If we do that and click OK, you'll get something that looks a little strange. So you'll get a graph that looks something like this. You're going to have male participants and female participants, and they're essentially going to be 2 straight lines because it's showing fake data. You're either a male participant or a female participant. So we got 2 lines of data going across our page. You might look at this and be like, well, hold up. How am I supposed to do a line here? Is this linear? Do I pass this assumption? This is why linear regression is tricky when you have categorical predictor variables. So some guides you might find, including the Laird guide, actually indicate that you can only use continuous predictor variables, and you can't use categorical variables in regression, which is not strictly true. So it's tricky to check something like linearity with categorical variables. We can make a graph. There's not much here that you can actually do to be able to indicate, does this work? Are we allowed to use this? So put this one in your back pocket. It's tricky with categorical variables, but we can still check both of our predictors with the outcome variable in a graph and say, if we combine these factors, what does that look like? So we can go back to our chart builder and we can set it up in a way that looks like this. We've got our dependent variable or our outcome variable, which is fake data 1 on the y-axis. We've got our continuous predictor variable, which is fake data 2 on our x-axis. And we've put our categorical predictor variable up where it says set color. So in the top right. Here, I'll put my laser pointer on so we can see this. So we've got our y, we've got our x, and then we've got our categorical predictor variable up here. This works if you have like a fairly simple data set. If you've got, let's say, a multiple linear regression with like 3 continuous variables and a categorical variable, this is not going to work. So this works today because we're doing something simple. If we make a graph like this, what this will do is it will take that first graph we made, which has fake data 1 and fake data 2, and it will color coordinate based on our categorical variable. So here we've got blue dots for the male participants, and we've got like these pinky dark purple dots for the female participants. So similarly, we can squint at this and be like, okay, if I was to draw a line of best fit through the blue participants, does that look like a straight line? And if I was to draw a line of best fit through the female participants, does that look like a straight line? So that's what we're talking about when we're doing linearity. Here again, it looks a little bit like a U, both for the male and the female participants, so we might not have met the assumption of linearity. So again, for practice today, we're going to run the test anyway. But this is a warning to always check your assumptions because you don't know if you've met your assumptions unless you've actually checked them. All right, reminder, our last 4 assumptions we check when we actually run the regression. So what we have to do next is build our regression model and then remember to check those last few assumptions. So how do you actually run a multiple linear regression? You click Analyze, Regression, Linear. So what we're going to do is we're going to build our model, check our assumptions, the last 4 that we have to check, and then actually interpret the regression itself. So Analyze, Regression, Linear. That will open up the linear regression dialog box. You're going to take your dependent or outcome variable, fake data 1, and put it in the dependent box. And you are going to take both or all, if you're doing more than 2, of your predictor or independent variables and put it in the independent box. So here we're going to put fake data 2 and gender. There are a few other options you need to select. So you're going to click Statistics, which will open up the Statistics dialog box. And you're going to make sure we've got estimates, confidence intervals, model fit, and descriptives selected. And importantly, to check our assumption of multicollinearity, you also need to click the box that says collinearity diagnostics. So we have 1, 2, 3, 4, 5 things selected here. Once you've selected all that, you can say continue. Reminder at this stage, also, for the independent variables, if you have a categorical predictor variable, they must be dummy coded. So if you had 5 different categories, you would actually be including 4 independent variables in your independent box here. All right, after you've clicked Statistics, you're going to click Plots. This is again to check one of our assumptions. We're going to take Z predicted, and put it on X. And we're going to take Z resid or Z residual, and we're going to put it on Y. We're going to make sure we click the buttons that say histogram and normal probability plot. And then we're going to click continue. So this will make a graph that we can look at. And then one more thing we have to click. We're going to click save. Save, what this does is anytime you do something in the save dialog box, it will actually save something to your data window. So it's going to create a new column of data for you. We're going to ask for standardized residuals. We'll use this to check normality. And we can click continue. Once you have done all of that, you've clicked everything you need to do. You've moved all the pieces that you need in the main dialog window. You've clicked statistics, you've clicked plots, you've clicked save. You're ready, you can click OK. The first thing we are going to do is now that we have built our model, we can check our remaining assumptions. So this is assumption number 5, homoscedasticity, $5 word. We can scroll down to what is called the residual versus fitted plot. On the y-axis, I'll make sure we've got our cursor. On our y-axis here, we have regression standardized residual. And on our x-axis, we have regression standardized predicted variable. So what we're doing here is we want to look at the left side and we want to look at the right side and say, do we have approximately equal number of points? Yep, looks pretty good. We want to look at the top. We want to look at the bottom. Do we have an approximately equal number of points? Yep, that looks good. Is there a specific shape or are they just randomly dispersed? We are looking to see, are they random? If you have some kind of cone or V or fan shape going on, you have failed the assumption of homoscedasticity. Here we see no obvious pattern. We're okay. We've passed this assumption. Excellent. So move on. Our next assumption is multicollinearity. We can scroll to the table that says coefficients, and we can ignore everything except on the very far right, there's a section that says collinearity statistics. With multicollinearity, it's a fancy term that essentially says your two variables might be accounting for the same variance in the model. They're doing the same job. For example, height and weight might explain the same amount of variance in some model. So you might have to remove one of those variables because having both of them in the same model might be overinflating how well your model is doing. So we can look at the collinearity statistics section to say, do we have multicollinearity? Here, if we look under the VIF column, we can use VIF, variable inflation factor, to determine whether we have multicollinearity. If you have a score like 3 or less, this indicates very low correlation between your predictor variables. If you have a VIF score of 3 to 8, this indicates some correlation or a potential risk of multicollinearity. And if you have a VIF score of greater than 8, I would say you have pretty high correlation and you most likely have multicollinearity, and you might consider removing one of the variables with a very high VIF score. The exact thresholds might vary by your field of department, so you can always check in if you've got an advisor, ask them if they know about VIF. But generally, anything above 5, you might be at risk. All right, so that's multicollinearity. Here our scores are both close to 1. We've passed the assumption of multicollinearity, no problems. All right, assumption 7 and 8, we need to check the residuals. So in our data window, we should have a new column of data that has just been created because we clicked the save option. And we're going to check to see in our residuals, do they look approximately normally distributed, and do we have any outliers? You've seen this before if you've come to my workshops. We click Analyze, Descriptive Statistics, Explore. This is one of the options that's kind of hidden in SPSS, but we can use the Explore procedure to look for both outliers and normality. So let's do both. What we do is we take our ZRE_1. If you're doing a lot of regressions at the same time or in the same SPSS window, the number will increase with each regression you do. But if you're only doing one at a time, this will be called ZRE_1. We put it in dependent list and we click the plots button. You're going to uncheck stem and leaf and check histogram. And you're going to check normality plots with tests. Once you've done that, you're going to click continue and then you can click OK. And this will check both normality and outliers. So let's do both. Okay. If we scroll down to the test of normality table, this gives us a statistic to be able to tell us whether we have passed normality or not. If you have 50 or more observations, you're going to look where it says Komglemerov-Smirnov. Here we have less than 50 observations, so we're going to look on the right-hand side of the table where it says Shapiro-Wilk. Our Shapiro-Wilk statistic here is 0.465. Because this is greater than 0.05, we have passed our assumption of normality. No problems. If our p-value is less than 0.05, it means we have actually failed normality. Our residuals do not pass this assumption, and we maybe shouldn't be using this test. Shapiro-Wilk is a statistic that you can use. There's another way to check normality as well. This is called visual inspection. So if you've clicked everything that I have today, you should actually have 2 different versions of this histogram. They're the same thing essentially, but one has the normality curve, like that bell-shaped curve imposed on top. And you can squint at these a little bit and say, do they look like that typical bell-shaped curve? Here it's not bad, it's not perfect, but I would say this passes visual inspection. There's one other graph you can use for visual inspection. It's called our QQ plot. Here we're looking to see, are those points pretty close to or on the line? Here I would look at that and say, yeah, those points are pretty close to the line. I don't see any weird like pulling away. I don't see any weird straight lines happening. This looks pretty good. So using our statistic and our visual inspection, I would say we passed normality today, so we're good to go. If we scroll to the bottom of that output, we should also see a box plot. There are multiple ways to check for outliers in SPSS. SPSS makes the outlier box plot method really easy. So what we're looking for here, this is again based on our residuals. We have plotted our residuals. We've got our median, our interquartile range, our whiskers. We're looking to see, are there any data points outside of those whiskers? A circle with a number would tell you that that row of your data set is an outlier. A star with a number next to it would tell you that that row of your data set is an extreme outlier. And you might want to consider removing those because outliers and extreme outliers can skew your analysis. Here we have no outliers, so we've passed this assumption as well, which means we are now allowed to interpret our regression. All right. So if we scroll to the section that says model summary, this is the first part that we are going to look at for our regression analysis. And we're going to look where it says R-square. The R-square value tells you approximately how much of the variance is being explained by the model, i.e. you've built a regression. How much of what you've told it, how much of the predictor variables are actually helping to explain what's happening in your outcome variable. Here we have 0.091, so 9.1% of the variance of the outcome variable is being explained by the predictors you have given the model. Not bad. It's about 10. 10% is not bad. The next thing you want to look at is in the ANOVA table. You're going to look in the SIG column, significance. This is your p-value for your ANOVA. If your p-value is less than 0.05, you get a thumbs up, you get a green light, you are allowed to interpret your regression. Here our p-value is 0.274. This is greater than 0.05. This means we would actually normally stop here. We would not interpret our regression. Our model is not doing a good job of explaining what is happening. So normally we would stop here. For practice, I'm going to keep going. To actually interpret the regression, that's in your coefficients table. Again, normally we wouldn't interpret this, but for practice today we will. You're going to look in the SIG column. The SIG column is your significance. This is your p-value, and it tells you for each of the variables you have included in your regression, is it doing a good job explaining what is happening in your outcome variable. So we've got fake data 2 at 0.429, non-significant. We would not be able to say that fake data 2 is doing a good job explaining what is happening. And for our gender variable, we have a p-value of 0.127, again, non-significant. We would not be able to say whether gender is doing a good job. If these were significant, you could also look where it says unstandardized coefficients beta. This helps you quantify how good of a job or what this variable is actually doing when it is trying to predict the outcome variable. So for fake data 2, for example, 0.102 is the value under unstandardized beta. This would indicate, I've got some wording in our, there we go. So I've got some wording in the PowerPoint. So if you have the PowerPoint, you can follow along. Because the value is 0.102, this means that for each 1 unit increase in our fake data 2 variable, which is our predictor variable, this resulted in, on average, a 0.102 unit increase or 10.2% increase in fake data 1, which is our outcome variable, when accounting for gender. If we're looking at our gender variable, that value is negative 0.691. Based on our dummy coding, we know that men are coded as 0 and women are coded as 1. So if we say 0 times negative 0.691, that's our score for men, which would be 0. And if we have women coded as 1, 1 times negative 0.691, that means women have a negative score of 0.691. 0 is higher than negative 0.691. So female participants on average had a lower score, 0.691 units lower or 69.1% lower than male participants on our fake data 1 score when accounting for fake data 2. Generally, we don't interpret the constant line unless you're building a regression equation. If you're building a regression equation and you need help for that, reach out to me. But these are the most important pieces that you will probably be using if you're interpreting a multiple linear regression.